Today's Tesla AI Day was one of the greatest technology presentations since long time. It was super exciting to watch, even though here in Europe it was like 4 a.m. and now my brain feels kind of foggy. Tesla engineers presented their custom DOJO supercomputer. This chip will be training AI software, and then this software will be pushed out to the Tesla cars via over-the-air updates. In this video, I will be discussing the DOJO chip hardware in all the nitty-gritty details. First of all, I've already made one video about DOJO supercomputer 2 weeks ago, and I made some predictions based on this picture. So if you watch this video, you know that I was almost completely right. It feels nice. The key idea with DOJO was to make a chip which is specifically optimized for training of neural networks. Because right now Tesla is using general-purpose GPUs, which are obviously not fast enough. These GPUs will be next year replaced with DOJO chips. With DOJO, the goal was to build an easy, scalable computer so they can add as many cores as possible and to achieve low latencies, fast chip-to-chip communication. This is the D1 DOJO chip. It is fabricated at 7nm TSMC technology and it's pretty large. It is 645mm square, featuring 50 billion transistors. All of the area of the chip is going towards machine learning and neural network training. D1 chip consists of 354 identical nodes running at 2 GHz clock. Actually, Tesla ended up with the design in many ways similar to the series bus chip. It is actually a mesh of nodes connected by a high-speed fabric, which allows communication within one clock cycle. Each node has a machine learning compute and a CPU optimized around matrix multiplication. Also, each node got large and fast 1.25 MB as RAM memory. With a single node, they were able to achieve 1 teraflop of compute, which is pretty good. All these D1 chips, or so-called training tiles, are integrated into 25 dies using 3D package technology by TSMC. It is called Integrated Fan-Out System-on-Wafer technology. The key reason to use system-on-wafer integration is to preserve high bandwidth, so very fast chip-to-chip communication. These 25 dies are surrounded by high-bandwidth IOS connectors, which enable impressive 36 terabytes per second of off-tile bandwidth. This for sure suppresses the off-wafer bandwidth of series bus chip. This enables Tesla's system to scale out better than anyone else. Tesla claims that they can achieve 4 times better performance and 1.3 times better performance per watt. This tile outperforms anything from NVIDIA, Graph Core, series bus, Grok, Tenstorrent or any other AI training startup in performance and scale-up capabilities. This chip will be used to train models for recognizing different items from videos which are collected by cameras inside Tesla's cars. However, this chip is super modular. It means they could take a part of it and plug it in the car. However, I think for this application, power consumption of this chip would be too high to put it in any car. It appears that the total tile burns 50 kilowatts of power, while the chips are taking just 10 kilowatts in total. That's because power delivery, IOS, wiring, all of that is also drawing lots of power. Now, all of this power has to be supplied and cooled, and this is another challenge. Here is the picture of the complete system. Power comes in from the bottom, while the heat comes out on the top. I already discussed it in the details in my previous video. So the shiny piece on the top is a heatsink plate. Then below comes the compute plate with 25 chips and high bandwidth interconnect. The chips are actually facing down in this picture. In this system, Tesla delivers power to compute tiles vertically. The power supply modules with voltage regulators are sitting right beneath the compute plate, so it is reflowed directly into the fan-out wafer. So the advantage of this system-on-wafer technology is that it allows power integration directly on the wafer. Then power supply is followed by an interface section. Then there is a liquid cooling. This monster chip burns over 10 kilowatts from 52 volts DC supply, so heat dissipation is a real issue. So to cool it down, integrated liquid cooling is used. And then on the bottom there is power supply circuits. So in this system, power, thermal and mechanical are all integrated directly with chips into one system on wafer. This is how integrated fan-out system on wafer technology looks like. The key benefit of this technology is that it allows to connect multiple chips and power and directly attach them to the heat dissipation module using route redistribution technology without any need for a PCB. Packaging multiple chip arrays so closely has benefits, such as low latency means super fast chip-to-chip communication, and low impedance. Low impedance means stable power delivery and low power loss. And this technology was also used for a series bus system chip, which is called wafer scale engine, this super large chip which occupies an entire wafer. I was discussing it in one of my previous videos. With the scaling that Tesla wants to achieve with their DOJO supercomputer, there will be a huge amount of heat dissipation. Each chip has a breathtaking 400 watts TDP. TDP is thermal design power, so maximum amount of heat generated by chip. 400 watts is a really hot chip, and such a chip requires a really decent cooling. So this technology, integrated fan-out system and wafer technology by TSMC, is a solution to this. And guess what? This training tile is also modular. So what Tesla did next, they put together 6 of them in a tray and packed 2 of these trays in a cabinet. They call it training matrix. So there are like 12 tiles per cabinet, which gives a total of 108 petaflops per cabinet. In this way, we come to 400,000 custom cores and 132 gigabytes of SRAM. Those are really mind-blowing numbers. And the scalability of the system they developed is incredible. I'm just wondering how many more they can pack together. Since the system is so modular, without any interconnect bandwidth limitations, they pack together tiles into what they call an exapod. 10 cabinets providing 1 exaflop compute. It means it is capable of calculating at least 10 in the power of 18 floating point operations per second. I'm really wondering if there is a limit. To my understanding, the limit now is software, because I'm not sure if they are capable to efficiently distribute the compute over such a large system. They've also demonstrated the evidence of DOJO operation, so that it's actually running, but it all seems pretty fresh, like results from yesterday. So the DOJO chip is truly a monster, a very hot monster, and I'm looking forward to hear more on the Tesla's progress with DOJO system in the next months. Overall, Tesla AI Day was kind of a masterclass on AI, but they also introduced hydronets and humanoid robots, so-called Tesla bots. For sure, I will be making more videos elaborating on the new technologies which Tesla presented on AI Day, so not to miss it, make sure to subscribe. And please give this video a like if you enjoyed it. And now watch my another video where I explain the hardware of the Tesla full self-driving chip. I will link it here. And now finally I go to edit very fast this video and then I can go to sleep. So see you next week in my next video. Ciao!